All right, so welcome to the final lesson in this series covering functions and libraries. So this is effectively the beginning of a new section in the book site Intro CS of Princeton, but in the series it is a final lesson. So let's have a look about functions and libraries. So there'll be four sections covered, which is the basic concepts, a case study for digital audio, application for Gaussian distribution, and modular programming and libraries. So we've covered quite a bit with the basic building blocks for programming. We've done data types and assignments and math and text I/O, conditionals and loops, arrays, graphics, sound, images, I/O, and now we have a very important building block, which is functions and libraries. So what is a function? Well, a Python function, it takes 0 or more input arguments. It returns 0 or output value, may cause side effects. For example, output to stand and draw. Python functions are more general than math functions. So here's a very simple graphical representation of a function. You have inputs, does something, little black box, and you get outputs. Applications. So scientists use math functions to calculate formulas. Programmers use functions to build modular programs. You use functions to effectively do both. So example of functions we've seen before, we've had built-in functions already. We've had apps to find the absolute value, length to find the length of an array, for example, or a string, int to cast a string to an integer. Our own libraries we are familiar with, standard io.write, standard draw.line, standard order.play. And we've created our own functions already, like user-defined functions like main, the main function. So function definition, we have an input, we have something happens in the black box, our function itself, and we have output. So to implement a function, you need a function name, consider type and variable, type and declare name. Consider type and declare name of parameter variables. Consider type and specify return value. Implement a function body, something happens in the code, and finish with a return statement. So here is a representation of a function definition, what it looks like. We have the signature or how you create a function. So let's maybe create a file here to go through this .py, open up, and then we can better look at what this looks like. So we have def harmonic. So def is a signature, it was like built-in keyword. Harmonic is the name of the function. And then we have an input variable or parameter. Then we have a colon. And then we have a body for our code. Total equals 0.0. Again, pause this video, try this yourself. And then you have for I in range, and normal for loop, sorry, for I in range of 1 to n plus 1. N plus 1, pretty standard stuff here. And then a code block or a for loop plus equals 1.0 divided by I. And then we'll work out the return the total. So it works out the harmonic. So this is the name for a function. This is how we define a function. Our body code inside it, and this is the return. This is the output to our function itself. And this is importantly a local variable. It is only known within the function. It's not known outside your code, outside the Python file. Sorry, outside this function. All right, so that's the basics of of a function. Function calls. So to call a function, call its function name. You want to call it, you have to call it by its name, followed by the arguments or separated by commas, enclosed in parentheses. So if you want to call it in our code, if I actually want to use it, by calling we mean using. If you want to use it in our code, to say, well, okay, harmonic, and give it value 10. This is how you actually use a function. Call it by name, and then give it the input argument. When function finishes, the return value effectively takes the place of the function call. Okay, so let's see how this works. So if I say Python, let's bring this across so we can see what I'm actually typing here. So Python func the py should run, but nothing happens. I mean, the code does run, but let's actually maybe standard IO the right, standard input standard IO, with standard IO, and then let's maybe write the output. So print standard IO the right. Let's see if this actually does anything. It does. Okay, let me do a white line rather. So let's see something a bit nicer. I get a harmonic for the input value 10. I effectively get the return value. It returns as total, and effectively this value total is output here. Right? So how do we store this a little better? Let's maybe do output to function. Output of function is equal to harmonic 10. Like that. And then I take this variable, paste it in here. Right, I get the same result. So effectively what's happening is the code runs, the Python code runs and it sees this happens. It doesn't do anything with it. It sees I want to import Studio, send it IO, which I do. Then it gets to this assignment. It says, okay, well, I have a variable called output of function assigned to harmonic. So it sees harmonic.10 and the code jumps to this function and executes a function. It inputs 10 for n and works out the code body over here and then returns the value into total, which will be represented here and saved into output function and then printed here. That's how the code works. Pretty straightforward. Again, pause the video, try it yourself. And this is effectively what I've done here. And this is a little sample code showing the same thing. You can try it out yourself. My example, illustrates the same thing. It's the same thing. So control flow. So how does this actually work? Well, as I've just shown you, but the first iteration of the global, well, this is exactly what I've just shown you now. So your first iteration of the global for loop. So processes the import statements. Okay, so let's say, for example, where the import statements on top. There it is. Making the features defined in a modular available. So it's done. Okay, then the process defines the harmonic function, but doesn't execute the function. This is very important. It does this code, then it looks at this code and doesn't execute it. It just checks it, makes sure it's all correct, but doesn't do anything with it yet. Very important, right? Python executes the code line by line, but it can't do anything with it. It just sees it is defined. So then executes the first statement in global code, which is this one. Executes this first one, which is the assignment, right? This is the first thing it sees that it can actually do something with and performs a function, which is calling harmonic. And this shows initialize the variable parameter available to n to 1 minus n to 10 and starts doing the for loop. Goes in the function, does a for loop and works out total. Executes return statement, which is this one, and jumps back to this line over here. So this code, almost like the code is in limbo while this function is processing the output. Only when it's done, it jumps back to line 9 and gives a result, and then you print it out. So this is what these lines and arrows try to illustrate. So scope. So the definition of the scope of a variable is the code that can refer to it by name. So this is a piece of code that works out certain, it works at the square root. So in a Python program, a variable scope is the code following its declaration, the same block. There's a global scope in the program, such as that all functions in the program can access. Should you only use global scope for constant variables and name in all caps, for example, EPS. Two different method variable names need each with scope limited to single for loop. In this function, there are two different variables named I, each with a scope limited to single for loop. So this is very important. So here you have two variables, I for this loop and I for this loop, but it is unique, it is local, it is only known within this for loop, right? You cannot use it anywhere else in your code. Same with this one as well, it is only known within this for loop. So this is what we call scope. If your variable, where your variable is known it known within your whole code or not? So my example is a bit easier. You can, again, copy this code and type it out yourself to get see if it works. But my example is very similar. If I have a variable, if I have defined a variable x is equal to 10, this is called a global variable. Global variable. It is known throughout the Python file. Right, so I can say standard IO right line x and the total one gives me 10, right? So that's what x is. This over here, anytime you have a indented code like for loops, if statements, functions as well, it is anything inside it is local, right? Is local to that body of code, local to this code block. So this total value, total is not defined before. It is local to the function. It is not known in the rest of the Python code. Okay, very important. This is what we call scope, right? It's variable scope. So this is known as variable scope. So I can't do this. Well, let's try to see what happens if I say total. I want this work. It's going to give an error. It's going to tell me total is not defined. Total is not defined, but I defined it here. Here it is. But it is only known in the function. So I could do something like this. I can say, I can do that. It will work. It will print out 0.0, which it did over here. It printed out 0.0, which is that of total. But when it gets to this line, it says, no, I'm sorry. Total is not defined in the Python file. You cannot use it globally. However, you can print it out locally, local to this function only. Right? So that's the meaning. It's the meaning of scope. Again, you can try the example as well, but my example is very similar. Flow of control. So again, this just illustrates again the same thing that I've shown you already. The flow of control. Control transfers to the function code. So again, I said like the code is almost in limbo when it goes into until the function completes what it's supposed to do. So argument variables are declared and initialized with given values. The function code is executed. Control transfers back to the calling code. The return value assigned in place of the function name and the calling code. So again, as I said, to repeat this again. So the code runs, does all this, checks, okay, makes assignment, good, stores it in memory. Gets to this, it doesn't do anything here, it just checks the code is correct. It can do this though, and it performs this operation. It says, okay, the function has been called, it has a value of n, and the code stops. It does not continue here. It doesn't continue with line 20, 22, 24. It stops. And it goes to line 8. And it completes line 8 to 16 until it finishes, i.e. until the for loop is done, and then it completes line 16, Once it goes to line 16, it jumps back out to the main code, returns a value of 10, well, of total, which effectively, just oh, sorry, 0.92, whatever, so 2.92. This value, 2.92, is now stored into output function, and I'm printing output function here. And then there's the rest of the code, right? So this is the flow of control. Again, you can, this example code does the same thing. You can try it out yourself. Note that OS calls Python that then executes a global code in a Python file. The bottom if statement then calls the main function. Yeah, so this just, again, same example, you can try it out yourself, try and understand it. If you want to know more, let me know in the comments. But follows the same example that I've done here. Function call, they've done a control trace, how the trace works. Working out some Newton method, working on square root. So this is the different trace for the values, how function works. Oh, quiz. What happens when you compile and run the following code? For cube, well, it creates a cube of stars. So it looks like maybe this is a nice example to try out. Snify cube. So it works. So import standard IO. Sys. Okay, I want input arguments. Maybe not going to use that. It's, not too necessary. J equals I times I times I times I. Return 10J. Then define main. You really don't have to, not very necessary actually. I'm gonna not do it. In range. Let's do n is 3. There's 3. N is 3. 1 until n plus 1. For loop, standard I dot right align string I plus. I think it's actually going to draw a cube for us. That's string cube. Okay, let's maybe try to run this code. Let's zoom out a little bit so you can see what's happening. Define a function. Okay. Oh, this is wrong. This must be I. 10J, n is 3. I think it's going to draw a cube. Let's see what happens. Python cube. 1, 1, 1. Okay, this is output that it gives. Working out the cube. Okay, the cube for each number. 2 cubed, 3 cubed, and whatnot. Okay. What happens when you compile run the following code? We get takes in from a command line, or we just hard coded it, and it gives a cube. It's a very simple usage of create a small function to create a cube, or to cube a number. Quiz 1B, what happens when you compile and run the following code? So looks like the same. I don't return I. Oh, wait, they are saying I, and I. If this happens, that's the only difference I see. Let's see what happens now. Get the same thing. I think they're just trying to illustrate that the parameter you're passing is unique. It doesn't change. Same correct output, the parameter variable I is reassigned to cube result, but changing parameter value is confusing and bad style. Yeah, you shouldn't, you should rather define, like we've done before, like J. But I think what they're trying to do is illustrate to you that Python understands that it needs to be a new value used. I is used here and there as well, which isn't good practice. Try these J or something else. Yeah, I think that's all for that example. Up quiz 1C, what happens when you compile, run the following code, J's items, I. Well, it has no return function, as you can see. So nothing will actually happen. It will not return a result. We'll call the function cube I won't actually do anything. Returns none. So a logic error, need a return statement. Yeah. 1D, what happens when you compile, run the following code? Okay, it returns items, I. This should work, I think. It's a bit neater. This code works. This code's a bit neater. So we're going to say this one. So just removing a J assignment. I think this should work. Yeah. This makes code a bit more efficient. It works fine. Preferred, but more compact. So, okay, that's it for the basics. Now we're looking at a case study, digital audio. So sound is perception of the vibration of molecules. The musical tone is a steady periodic sound. Pure tone is sinusoidal waveform. Western musical scale A to 440 hertz, 12 notes in a log scale. Okay, some theory behind it. Digital audio to represent it as a wave, sample at regular intervals and save the value in an array. Okay, so we've done this before, playing around with input output with audio. This is a CD standard. Bottom line, you can write programs to manipulate sound arrays of float values. Standard audio library, developed for this course, but also broadly useful. Play a sound wave, which is typically or effectively an array of double values on your computer's audio output. Convert to and from standard.wav format. And here it is. The various examples, we've seen this before, to play various file formats. Enables you to hear the results of a program that manipulates sound. Hello world for standard audio. Okay, so again, I'm not this is a virtual video studio code environment, so it actually won't work. But so you can't actually hear anything. But this example again just shows you how we first and foremost create a math function for a sine wave. This is the sine wave math function that's been created, which is effectively 2 pi divided by 45 100 hertz. This is a math function which is created because audio wave is a sine wave. So effectively, we're using a math function to create a sine wave, and this is how you create it. And this is the function that we created for. Read a list of tones and duration from standard input. So this is how you read in data. Read in tones, they have a way to read in data from this elise.txt file. These examples are in the Princeton notes if you want to know more about it. You can try and play that on your own. What sound does the following program produce? PDF functions of 2.py. You can try, pause the video, try it out yourself. See how it works. What sound does this one follow produce as well? Again, you can pure noise. You can try it out and see what you get. Okay, that chord, produce chords by averaging waveforms. So you can you can superposition, which is when you add two sine waves together, you get a new sine wave. Just make sure it needs to be scaled, which is what they're doing by dividing by 2.0. But if you add two sine waves, which is how music is actually created, different chords are added together until you get one. So here, effectively, we're creating two arrays, A and B, adding them with some weight, and then you get the result. So this is how you can play a chord. And this is a function you can try and play that on your own. Play the tune, function to add harmonics to a tune. So this is different ways how you can superimpose or superposition, add two different arrays based input values. Digital audio summary. So this is a summary of it. Bottom line, you can write programs to manipulate sound. Select shows case study of the functions. Upcoming assignment, function musical tones and notes. Okay, application for Gaussian distribution. So a Gaussian distribution is a mathematical model used successfully for centuries. Bell curve fits experimental observations in many contexts. Here's the equation for it. It's used. Gaussian distribution in the wild, polystyrene particles in glycerol, calibration of optical tweezers, laser beam propagation. polarized W bosons from top quark decay, cytochrome oxidase patches, many examples. German 10-mark note used to have the person, I think that, used to have this on it. Germany off by a factor of 10 sigma. Defining a library function. So is a Gaussian PDF file implementation in Python library? No, it's not. You cannot use it. Well, it's not there. Why not? Maybe because it is so easy for you to do it yourself. So this is how you can define your own phi function by creating a math expression minus x times x divided by 2.0. So here, this function over here, zoom in a little bit, 1 over square root 2 pi times the exponent e to the minus x squared divided by 2 is very easily represented by this math expression in Python. Minus x times x divided by 2, mass divided by mass square root 2 pi. In your PDF, it's also worked out quite easily. Return phi x minus mu divided by sig divided by sigma. So you can try this out as a good experiment to understand how you can write mathematical expressions, Python. Functions are an easy way for any user to extend a Python system, which is true. So Gaussian cumulative distribution function. What percentage of the total is less than or equal to z? Equivalent, what is the area under the curve of flat curve left of z? Gaussian cumulative distribution function. These are functions you can work out these questions. Typical application, SAT scores in this year required at least 820 for Division 1 athletes. What fraction of test takers did not qualify? And you can work out quite easily with Gaussian distributions. Gaussian CDF implementation, no closed form for Gaussian CDF, how to implement. Oh, here's a nice Taylor series. Defining the process for the Taylor series, the function for it. Defining some conditions for Z, and then working out a while loop. You're working out a sum with a while loop, which was done before. We've done working out summation a lot of times with while loop. So there's another example of it. Bottom line, Taylor series goes to infinity, stops when close enough to numerical integration. Bottom line, 1,000 years of math formulas at your fingertips in Python. Very cool. Summary, a library for Gaussian distribution functions. Best practice, test all code at least once in main. Also have it do something useful. What fraction, for example, of SAT test takers did not qualify for this test in a certain year? You can try it out here and get the results. Fun fact, we use CDF to evaluate randomness in submitted programs. Bottom line, you can build a layer abstraction to use in any future program. So try this code for yourself and see what you get. Exercise. Write a static method odd function that takes 3 Boolean arguments and returns true if an odd number of arguments are true. So here is the function that's given. They're using a modulus to work that out. We've, I think, done before in previous lessons how to work out if a number is odd or even. But now we are just taking in, or writing a function to the same thing with 3 Boolean arguments. Sigmoid, write a static method sigmoid that takes in a double argument and returns double value obtained from the formula. Here's a formula you need to do. Try it out in your code. Here's a very simple sigmoid function expressed in Python on 1 plus math.express to e to the minus 1x. Max3, or just that's it, right? A static math max3 method that takes in 3 int arguments, returns the value of the largest one. Add an overload function does the same thing with 3 double values. So how do you work out the largest of 3 numbers? This is the approach that they follow. Again, stop the video, try it yourself, make sure you get the correct result output. Right, modular programming. So functions, libraries, and modules. Modular programming. Organize programs as independent modules that do a job together. Why? It's easy to share and reuse code to build bigger programs. Facts of life. Support of modular programming has been a holy grail for decades. Ideas can conflict and get highly technical in the real world. A program is a set of statements with standard input-output. A function is a set of statements with defined input-output. A module is a set of related functions for use by the programs. A library is a set of related modules for use by other programs, for example, Pygames. A client is a program or function that uses function in other modules. So this is the order of hierarchy, you can put it that way. You get a program, then a function, then a module, then a library. So a library is a collection of modules, a module is a collection of functions. A function is a part of a program. So then we look at modules, implement data types. Stay tuned. So fundamental abstraction for modular programming, we have a client, we have an API, we have implementation. So API we are quite familiar with. Even with standard I/O, write line and whatnot, we've used it before. So a client calls a module's function, for example, Gaussian plot. The API interface has been set up for PDF and CDF, for example. Implementation is a code module, right? Doing the PDF and working out what to do. So a library, how does a library work in terms of programmatic flow? So here's a line of code here. So I run this code, Gaussian table.py. So what does it do? Well, there is another file, a module, called Gaussian table.py that has imports, the for loop, does all this stuff. This is represented by the client. This is what the client needs to do. All right. And then this, once you see Gaussian CDF, it goes to this file over here, which sees, okay, there's a file called Gaussian over here. Let me get my pointer. There's a file called Gaussian. In Gaussian, there is a file called CDF. So there's a function called CDF. That's why we're saying Gaussian.cdf. It says go to the file Gaussian, find the function CDF, input these three variables, these three parameters or arguments. It works it out. All right. And then it sees, okay, but at the end of this function, we need PDF as well. So it actually jumps into another function, right? This is like in a limbo. So then before it finishes this function, it must jump to another function. And it does this function and works out the square root and everything else it needs to do and runs, sees, okay, I need to go into another module because I need to work out the exponent and the square root. So it's in another module completely now, the code. The current code that's been run at runtime, it's in another module working out square root. Once it's worked out the square root over here, it goes back and gives a result. Then it goes back and works out the sum. And then goes back to your main code and finally gives a result. So I'm not sure if these arrows might be confusing, but this just shows you how to modularize code, right? Not have everything in one file, but to have everything separate modules, as in Gaussian.py and the math module. Yeah, so maybe pause the video, try to understand what I said, and look at the arrows and see how it works all together. So I think I didn't miss anything yet. Okay, so standard random library. So again, this is developed for the course by Princeton. It implements methods for generating random numbers of various types, available for download at book site. Again, so we can use standard random. I think I've used the normal Python random library already. So this is unique standard random you can use as well. First step in developing a library, articulate the API, right? Articulate the API, tell people how to use the API, tell people how to use the functions. Standard random details, this is how uniform works. Uniform float to create a random uniform float variable. You could implement many of these methods, but now you don't have to, right? It does it for you. Stress testing, program does not crash when client doesn't follow contract. Indeed. So this is what the client inputs. This is what he writes. And then, as we've tried to explain before, you see standard it jumps to this code. It jumps to standard random module, finds a function called Gaussian, implements it, and exports it, and draws this plot over here. So again, another example of the library. I think there's a duplicate, as a duplicate slide over here. So one way to generate a random number, take from Gaussian distribution, you see the box Muller formula. Okay, again, this is practice for you. Try this out in Python to type it out. Sine times square brackets, math 2 by v times by square root minus 2 log of u. And here it is given to you using the math function math.sine 2 times pi math.pi, because pi is built into the math function, math library, times v times math to square root minus 2 times math.log u. Best practices: have small modules, separate and classify small tasks, just like we created the cube function. This might seem trivial to create your own cube function, but allows you to reuse the code very quickly, very easily, right? Instead of having this typing it out all the time, you can just call cube when you need to. And this implements a layer of abstraction. It also allows you to make your code independent development, code client before coding implementation, anticipate needs of future clients. Test clients, include main test client in each module, do more extensive testing. This is a good approach in general. Standard array, this is what we've seen before. Create 1D arrays and read floats and write 1Ds. So these are the different, this is the libraries you've seen before, right? So if you use standard array already, this is showing examples of how, it's illustrated and how to use it. Input conversion, how things can be converted, different file formats for arrays. So Princeton, this is drawing fractals. This was a pretty cool example I've actually done before. Let me just check what I have over here. Also, actually, like this fractal examples is going to be one about a leaf as well. So I've coded my own one, which is very similar. There's not much difference. Just how it's coded. But they're using standard random, discrete, and standard array to create this. I've done this too. Again, you can copy this code here, or you can try it my own as well. So I could use chaos. It's also used random, very similar setup for CX and CY. Here I'm actually using a list. I'm not using create a 2D array, and then working out with standard draw. So again, I cannot draw it as a pop-up image, so I'm saving it, and then I should get an image of this triangle. So you can try this out. Very similar approach to working out X and Y over here, and then drawing all the points. So let's see if that works out. Let's run it. Chaos. This index out of range. Why is not happy? Oh, it needs like a input. So I think it's like 10,000. Let's do 1,000. You'll see that it's not enough points from image. It's getting there. That's not enough random values. That's 10,000. And there we go. Nice. A nice fractal drawing of triangles. So very cool. Barnsley Fern, this is one I also really like. You have to define these functions, which we've done already in my code over here. This is the Fern function. Define the various functions for the Fern, for the various probabilities, 0.86, 0.01, 0.93, for the left and right leaf. So this I think is pretty cool. I'm gonna run it. Also need probably 10,000 runs, 10,000 like that. And let's see what we get the Fern. Very cool. I really like this little example. Let me do more than 100,000. See how that even gets it even clearer. High resolution. Very cool example. Try it out. You can use my code as well. Here it is. Pause the video. try it out if you want, or you can try the code. Oh, they don't actually give the code for you. They can take my code as well, pause the video, type it out yourself, and try it out. This is, again, a walkthrough, so try and do it yourself. I'm saving it. You don't have to save it as an image. All right, so moving on, there's a stats module as well that you can use for various examples. Implements methods for computing statistics on arrays of real numbers. Available for download, but if you install the library, I mean, it's installed by default. Easy to implement, but easy to use. So working out mean and standard calculations is quite easy. This is the mean and standard deviation, sample variance for the some numbers. You can work this out by hand if you want, or you can do this in Python very easily using a stats module. So you can also work with the variance as they're shown here. This is actually ways that they show how to work out your own mean and work out your own standard deviation. Work out your own median. You can work out it all over here. And this is an exercise to work out how do you work out variance. Here's a code. First work out mu, work out the mean, and then do a sum. All the values and divide the total, divide the length of a minus 1. Work out the variance. So plotting, you can also plot using standard draw. Again, there are actually better ways, or not more, not so better, but there's a library called matplotlib that is built into Python, very well established for drawing and plotting. I would prefer to this, but again, this Princeton course wants you to use their own libraries for certain reasons. So try out this code and see if you can plot these various plots. Modular programming, standard stats, standard random, and Gaussian client, flipping coins, how many heads. Again, we've done this example many times. Working out a binomial function, getting a binomial function, and then working out a Bernoulli. There's always in all statistics functions to run to work out predictions and whatnot. Example of modular programming for Bernoulli trial. So here's a function, a file with the main function. Here is a standard random binomial function that's called, and then works out the norm and phi variables and works out the Gaussian PDF. So the Bernoulli simulation gets command and input, run experiments, keeps track of the frequency of occurrence of each return value, normalizes between 0 and 1, and plots the results. So I can try it out as well if you want. Dependency graph. So this enables development of complicated programs via simple independent modules. So dependency graph for the clients and modules in this section. So this is useful to see all the different modules that you're using when you're coding. Why a modular program? Why do we have all these functions and libraries? So allows you to have independent development of small programs. Every program that you develop, there's an abstraction, self-documenting code. So the more modular code is, the less you have to document. It's self-explanatory. Separation of client from implementation benefits all future clients. Contract between implementation and clients benefits all past clients. Challenge is how to break tasks into independent modules. That is a real task. How to specify API, right? This is a real challenge and a real exercise. So here's a module exercise to compute the hyperbolic trig function based on definition given here. Because it's analogous to the standard trig function. So literally creating your own module that does the same thing. And here's the code for it. Again, pause the video, try it yourself. That's good practice for you. And that's it for this lesson. Hopefully, and this section as well. Hopefully you learned something. Until next time, goodbye.